In this video we're going to be looking at energy in ionic compounds and how the energy changes involved in forming these compounds have an impact on the strength of the ionic bonds. So let's look at the formation of ionic lithium fluoride from its elements. And so its elements in their natural states are solid lithium and gaseous F2. So in the final step, we want the gaseous ions Li plus and F minus to come together and form the solid lithium fluoride. And that step will correspond to the lattice energy. Remember that the lattice energy is the change in energy that takes place when gaseous ions come together to form an ionic solid. So to do that, we need to get both of these in their gaseous ion forms. So the first step is the sublimation of solid lithium, turning it from a solid into a gas. And so this energy change of sublimation is positive 161 kilojoules. The next step is to ionize the lithium, which means taking away one of its electrons. So this energy change is the same as the first ionization energy. Remember that ionization energy is the change in energy that happens when you take away an electron from a gaseous atom. So again, this change in energy is positive. So now we have the gaseous lithium ion. So now we need to get the fluorine ion. So to do that, first we have to break the fluorine molecule because here it's F2. So the energy needed to break this FF bond in F2 is the same as the bond energy, which you can look up in a table or something. So here we have half a mole of F2. So the change in energy for this step will be half the bond energy, because the bond energy is for 1 mole. So now that we have a fluorine ion in the gaseous state, we make it, or the fluorine atom, we make it into the ion by adding an electron. And so remember, the change in energy when you add an electron to an atom is the electron affinity. So for fluorine, the electron affinity is negative. And then the last step, now that we have a Li plus and F minus ions in the gaseous state, they come together to form the solid lithium fluoride. And this step is the lattice energy, which is, as you can see, it's very exothermic. So overall, the process of forming lithium fluoride from its elements is highly exothermic. And this is basically due to the very negative lattice energy, because if you look at these first steps, most of them are endothermic, which is unfavorable. But the exothermic lattice energy makes this process possible and makes it so that overall lithium fluoride is a stable compound. So the more negative the lattice energy, the more stable the ionic compound will be. And lattice energy can be represented by this equation. You don't really need to know this, but the two important things to take from this equation are that the lattice energy increases as the charges on the ions, which are Q1 and Q2, increase. And the lattice energy also increases as the distance between the ions decreases, which is the in this equation. So here we have two compounds, and we want to figure out which one has the more negative or more exothermic lattice energy. So first we have NaCl or KCl. Now the charges on all of these atoms are the same. Na and K are both +1, and the Cl's are both -1. So to do this, we have to look at the size of the ions. Now since Na plus is smaller than K plus, that means the distance between the Na and Cl ions inside NaCl is smaller than the distance between the K plus and Cl minus ions inside KCl. So since the ions in NaCl are closer together, according to this equation, the lattice energy will be greater. So NaCl has the more exothermic lattice energy. Here we have magnesium hydroxide or magnesium oxide. So first you want to look at the charges. So O2 has a charge of 2 minus, and then the hydroxide has a charge of 1 minus. So since the O has a greater charge than hydroxide, magnesium oxide will have a larger lattice energy according to this equation. So next, let's look at these energy changes. So we can see these are the first and second ionization energies of magnesium. We are taking away an electron. And so notice how the second ionization energy is much more endothermic than the first ionization energy. And then these two equations are the electron affinities for oxygen. We are adding an electron to oxygen. So the first one is exothermic, but the second one is highly endothermic. So to add a second electron to oxygen and take a second electron away from magnesium takes a lot of energy. But we know that magnesium oxide has the Mg2 plus and O2 minus. So if it takes so much energy to get it from 1 plus to 2 plus and the oxygen from 1 minus to 2 minus, why does magnesium oxide form as Mg2 plus and O2 minus? This is because of the charges. The 2 plus and 2 minus are double the charges of the plus and minus. So the lattice energy will be much greater. So even though the steps in formation are very endothermic, overall, due to the more exothermic lattice energy of this Mg2 plus and O2 minus, in the end the formation of this compound is more exothermic and more stable than if it was Mg plus and O minus.